Okay, good. So hopefully that'll be what's at the beginning of the thing there. All right, on the grid below, sketch a graph. The acceleration as a function of time for the object. Label the scale for the acceleration. Okay, so obviously acceleration is the what of this graph? That's just the slope, right? Acceleration is the slope of the v versus t. All right, so this slope right here is what, 2? That's 0, obviously, and this is a rise of -5 over 10, so that's -1/2. Okay, so then over here, you just have to make sure you do something like, I don't know, something like this. And then for the first 5 seconds, I'm just gonna make this 2, so like that. The next 10 seconds, like this. And then for the final 10 seconds, and then I'd label that 1, I'd label this -1.
That's all in here.
You're not taking AP test, right? Or are you? This one.
Oh, no.
Okay. Sadly, me changing your attendance status will be on the recording.
Is that recorded too?
Yeah, for eternity. Okay. Any questions on this first part? Pretty straightforward. Do what? Oh.
The top is 2. No.
Oh yeah, put that in. Okay, good, thank you. Yeah, I actually made the space for 2 and labeled it 1, so thank you. Any other questions there? Make sense? Everything good? All right, clear that off. Head down south as it were. Calculate the position of the object at t equals 5 seconds. The easiest way to do that is just area under the curve. Yes? It's just this area. Because that area, this area is equal to velocity. Oops, that looks like v of t. That's going to look like the cross product. All right, let's do velocity times time. Because velocity times time is displacement, right? Okay, so all we have to do is just count the blocks. 1, 2, 3, 4, 5, 6, and then this is 25, right? And then this is also 25, and then each of these blocks is 5 by 5, so it's just 25, 25, 25, 25, 25, 25. So 200, right? Yeah.
What is this for? It
This-
says 5 seconds.
This is, oh, did they say 5 seconds?
Yeah.
Yeah.
Okay, well that's even easier, because that's just 25. Okay,
Sorry.
this is the 2008 AP exam. We're doing questions 1 and 2, which was the homework last night. Okay, so yeah, so then that would just be 25 meters. But you see the idea for the whole thing. On which segment of the graph is net force acting on the object 0? So the net force should be 0 here because there's no acceleration, right? For 0 to 5 and for 15 to 25, I think there's accelerations on both of those. Calculate the net force on the object during the first 3 seconds. So we know that during the first 5 seconds, the acceleration is 2 meters per second squared. So what's the mass? 4 kilograms? 0.4. Okay, so the mass is 0.44 kilograms. So that's a no-brainer. We have 0.88 newtons, right? Or unless, sorry, 0.40? 0.40. Oh, so that means 0.80. Okay, good. Okay. Now, what could make this different? What could make this bigger? So here's the mass. There's the block. This is 0.4 kilograms. and then it's accelerating 2 meters per second squared, right? So there's some force we're going to apply. What would make this force bigger? What if I added something to this situation? Not more mass, but what could make this, like let's say if this is 1 Newton. So I tell you the force applied is 1 Newton, but that is the acceleration. What must be true? Well, think about this for a second. If you have to apply more force than is necessary based on the acceleration, then what must be going on? Clear speaking. Hey. Okay. The problem is I have the senior game and I have to get ready for that. Okay. Okay. I mean, if it comes down to there's absolutely no one else, I'll try. But yeah, thanks. Goodbye. Okay. So I'm pushing a box. I'm pushing the box forward. The box has a certain mass. The box has a certain acceleration. The force that is being used up to accelerate the box is just ma, right? Now, if I'm pushing harder than that force, there must be a force in what direction? Yeah, there must be a force this way, right? You see this? There has to be something pushing backwards. And how big is that force? If there was a force backwards of 1 Newton, how fast would this be accelerated? 0, right? It's not going to go anywhere. But do you see that if I'm applying forward 1 Newton, but it's only accelerating at 2 meters per second, that means I only needed 0.8 newtons to move this. So where did the other 0.2 newtons go? Probably friction. You see what I'm doing there? So I'm just trying to kind of flip it a little bit and let you see how this problem could be sort of dressed up, if you will. Okay. All right, so then calculate the work done on the object by the net force during the first 15 seconds of motion. The net work done is simply going to be the force times that distance, right? And then, so you could, or you could be sneaky and figure out the final velocity and then do it that way. Do we know the final velocity? Oh yeah, so there you go. The final velocity in the first 15 seconds was 10 meters per second. So we know that it started at 0. So if it got to here, then that means the work done must have been 1/2 mv squared, right? Now this is a perfect system where there's no friction, and what's happening, how much work is being done right here? How much work is being done right there? Michelle, what's the definition of work?
The amount of stuff happening.
Okay, that's a generally correct way to think of the amount of stuff that you're putting in to make something happen, right? What's the equation? W equals.
Is it something plus something else?
It's something times something else. Think about when you work out, right? What do?
You exert
Exert what?
energy.
You use up energy, but when you exert.
Sweat.
All right, so work is force times distance, right? How much force are we applying here? Yeah, 0, right? Because there is no acceleration. So basically what happened is we pushed this object up to 10 meters per second and we just let it go. Now it just slides by itself. So the amount of energy that it had here is exactly the same as the amount of energy it had there. Does that make sense? Okay. Here's a little fun thing. If this had the friction, like we talked about in the last thing where I had 0.2 newtons of friction, what would happen to this part of the graph? Yeah, it would slope down like this. Does that make sense? There'd be some little amount of friction going on there. And in fact, probably that's what the designer of this problem probably was thinking like that. Like you push it, it slides, and then it hits a friction patch. It slows down. All right. Oops. Okay, so we figured out that the amount of work done by the object is 1/2 mv squared. So 1/2 m was 0.4 kilograms, and then v was 10 meters per second squared, right? And so then that becomes 50 times 0.4 is 20, something like 20 joules. And then for the interval of 15 to 20, is work done on the object by the net force negative or 0? So of course we'd say 0, and that's because A is 0. Therefore, what? Oh, just kidding. I was on that 10 to 15. No, 5 to 15. Sorry about that. Yeah, so the 15 to 20, so that you don't forget the way I did, is that one, right? It's this section right there. And then that work is going to be negative, because negative work means you're trying to slow it down, right? So then you'd say, what, since A is negative 1/2 meters per second squared, therefore the force is negative 0.20 newtons, I think, and therefore the work, which is force times distance, is equal to negative whatever. Therefore, okay, does that make sense? Questions? Okay, good. Got that one done.